Hello, we are Team Fourier Intelligence. I am Ronak with my Rudra, Siddharth, and Sayantan. Our project is Acoustic Grid AI. In short, it's a system that listens to infrastructure, pipelines, switchgear, and uses acoustic signals and AI to figure out if something's about to fail.
So, the silent threat. Here's the problem. Hydrogen pipelines develop tiny microcracks over time, and it's called hydrogen embrittlement. And we can't see it initially, but over time it shows up. And of course, there's SF6 gas, which is used inside high voltage switchgear. It leaks slowly. However, the problem is that it is 23,500 times worse than CO2 as a greenhouse gas. Even small leaks are a huge environmental crisis. So the interesting part is both of these failures produce ultrasonic sound in the range of 120 to 180 kilohertz. There are existing tools as we can see in this slide, but the problem with that is they are either extremely expensive or the testing is accurate but it's a one-time offering, and handheld detectors sometimes of course need people to walk around and test all of these. This does not give you continuous and automated monitoring of the equipment.
So what does this project actually do? Four things. Edge sensing, STM32 microcontrollers with piezoelectric transducers physically listening at each node. Second, a central AI hub running a CNN transformer model to process everything. Third, spatial-temporal correlation. If multiple nodes hear the same event at slightly different times, we triangulate and figure out exactly where the problem is. And an LSTM model that tracks how the acoustic baseline shifts over weeks so we can predict failures before they happen. So this is the system architecture. Here's how it connects. Edge nodes, STM32 plus piezo sensors plus gas sensors do FFT and DSP right on the chip. We are not sending raw audio, just compressed spectral features. Those go over TCP through an ESP32 to our central hub, a Linux machine running PyTorch. The CNN transformer does the leak triangulation. The LSTM does fatigue forecasting. What makes this different from just sticking a microphone on a pipe? The hybrid architecture, edge nodes handle DSP, the hub handles AI, so each node stays cheap. Automated triangulation, the CNN transformer correlates signals across the network without any human involvement, and the LSTM gives us the actual prediction, not just detection. This is the big shift, from sending a technician out from something breaks to a system that tells you what's going to fail next.
Who would use this? Power grid operators with SF6 switchgear everywhere, hydrogen companies running pipeline networks, and regulators who need emission data. The impact is pretty direct. Catch failures early so nothing catastrophic happens. Reduce SF6 leaking into the atmosphere and cut down on manual inspection costs. Safer infrastructure, lower emissions, and lower costs. So here's a quick technology stack overview. In the hardware side, we are using piezo transducers, gas sensors including NDIR for SF6. In the software side, PyTorch for the models, First API for the backend. For training data, we are using COMSOL and MATLAB to simulate acoustic wave propagation and generate synthetic spectral datasets, so we can train without breaking real pipelines.
We will first develop a prototype of the hardware and then predict using LSTM fatigue forecasting, which is using AI. We are making critical infrastructure audible to human beings. That explains our name, Acoustic Grid AI.
The AI doesn't just detect, it tells you where and when.
We are Team Fourier Intelligence. This is Acoustic AI. Thanks for watching.